Dear students, last class we were discussing about work. We know that work can be classified into two types, irreversible work and reversible work. Last class we discussed about irreversible work. What are irreversible works? Work which take place in a single step. Work which take place in a single step. For example, if a piston move from V1 volume to V2 volume in a single step, rapidly in a single step, then those works are irreversible. Work equation to calculate irreversible work is minus P external into delta V. Last class we discussed about irreversible work. Irreversible work. So what are irreversible work? Work which take place, or when a piston move from V1 volume to V2 volume in a single step rapidly, then those works are known as irreversible work. Equation to calculate irreversible work is W is equal to minus P external into delta V. Today we are going to study in detail about reversible work. Second work, that is the reversible work. Reversible work. B. Reversible work. Now, consider a system or consider a cylinder filled with ideal gas. Let the cylinder be filled with ideal gas. Okay, consider a cylinder filled with ideal gas and a frictionless movable piston is attached to this cylinder. Okay, let V1 be the initial volume of the cylinder. Let V1 be the initial volume of the gas inside the cylinder. Initial volume. Okay, and let the internal pressure inside this cylinder due to ideal gas. So pressure inside this cylinder due to ideal gas, that is internal pressure. Let the internal pressure be P internal. Let the internal pressure be P internal. Now, if the pressure outside this cylinder, that is external pressure, if external pressure is, let it be P external. Let external pressure be P external. So, an ideal gas is filled in a cylinder fitted with a frictionless movable piston. Let the V1 be the initial volume of ideal gas and let P internal, pressure internal be the pressure inside the cylinder. Okay, pressure inside the cylinder. Now, let P external pressure be P external. Let P external be the external pressure. That is pressure outside the system. Okay, now if external pressure is infinitesimally greater than internal pressure. If external pressure is little bit, a small amount, infinitesimally means very small. So if external pressure is very small amount greater than internal pressure, it's very small amount greater than internal pressure. That is, you can write external pressure is equal to internal pressure plus dP. This indicates that external pressure is dP amount, that is infinitesimally small pressure. It is small amount. Okay, external pressure is little bit, a small amount greater than internal pressure. So internal pressure plus small amount pressure, small pressure change. Okay, so internal pressure plus that dP, very small pressure. Okay, when we add internal pressure plus dP, you will get external pressure. Okay, I think it's clear. External pressure is infinitesimally greater. Infinitesimally is very small, very little. So external pressure is little bit greater than internal pressure. So you can write internal pressure plus that little bit pressure giving external pressure. I think this is clear. I think this point is clear. External pressure is equal to internal pressure plus little bit pressure. When you add internal pressure plus little bit pressure, that is dP, a small amount of pressure, you will get external pressure. Because external pressure is infinitesimally greater than, little bit greater than internal. So internal plus dP is equal to external. I think it's clear. Now, here, since external pressure is little bit greater than internal pressure, the piston will move downwards because external pressure is greater, a little bit. Anyway, the external pressure is greater, so that piston will move downwards. Let the piston move here. Let the piston move till here. Okay. Now, again, if again after moving this much, if again external pressure is greater by a dP amount than internal pressure, again if a piston move till here, and again if external pressure is infinitesimally greater than internal pressure, again the piston move downwards. After moving till here, again if external pressure is little bit greater than internal pressure, it will move downwards again. Now again, if external pressure is greater than internal pressure, again the piston move downwards like this. If for example, if the piston move till here, let the final volume be V2. Now the piston has moved from V1 to V2, but not rapidly in the case of irreversible process. Here piston is moving very slowly by taking number of steps, right? Here in the case of irreversible process, piston is moving from V1 to V2 rapidly in a single step. That is irreversible work. But in reversible process, the piston is moving slowly, infinitesimally slow. By taking several steps, the piston is moving from V1 to V2. So here, in reversible process, work takes place very slowly. Infinitesimally slow, because irreversible process, it takes place rapidly in a single step, but here it is not taking place rapidly, it is taking so many steps, and the piston moved from V1 to V2 by taking so many steps slowly. That's why this process is known as reversible work which take place infinitesimally slow, very slow. Process which take place very slow, those processes are known as reversible. Those works are known as reversible work. I think it's clear difference between reversible and irreversible. In irreversible work, piston move rapidly in a single step, but in reversible work, piston moves slowly in each step and it reach from V1 to V2. Piston move from V1 to V2. I think it's clear. Now, what is the equation to calculate work done? What is the equation to calculate work done in a single step when the piston move from here to here? W is equal to minus P external into delta V. This is the work. This is the equation to calculate work when a piston move rapidly from V1 to V2. But here the piston is not moving rapidly from V1 to V2. It is taking so many steps. So the piston is taking so many steps. First it moves from here to here. Then it moves from here to here. Then it moves from here to here. So there are the piston is moving from V1 to V2 by taking so many steps. Let work done in each step be dW. Each step be dW. Small work. Here the piston move from V1 to V2 rapidly in a single step. Here we can see a large distance or large work, but in this case the piston is moving from here to here, so we can observe a small work. That small work be dW. D indicates small change. Here there is large change, so you can write W. But here the work is very small when the piston move from this step to this step. From here to here, the work is very small. The work done by the piston is very small. Let the work done be dW. Again, the piston move from here to here. Let the work done be dW. So, in each step, the piston is moving a small distance. So, each step dW work, dW work, dW work, dW work, right? So, work done when the piston moves from V1 to V2. So work done when the piston moves from V1 to V2, that is total work. W is equal to, so we have to calculate total work, that is work done when the piston move from V1 to V2. We have to calculate the whole work V1 to V2. That is dW, total work is equal to dW plus dW plus dW plus etc etc etc. We have to add all the work done during each step. We have to add all the work done during each step. I think it's clear till here. I'll explain once more. Please listen carefully. Now we are going to discuss. Work can be classified into two types: irreversible work and reversible work. In the case of irreversible work, the piston moves from V1 to V2 rapidly in a single step, and work is equal to minus P external into delta V. Large change in volume. Delta V is large change in volume. Large change in volume. Right? So W is equal to, since there is large change in volume, work is also large, right? Large change in volume, so work done is also it will also be very large. Now, second work is reversible work. In the case of reversible work, the piston, if external pressure is infinitesimally greater than, infinitesimal is very slow, very low value. So if external pressure is little bit or infinitesimally greater than internal pressure. If external pressure is infinitesimally little bit greater than internal pressure, that is external pressure is equal to internal pressure plus small pressure change, that is little pressure. Right? Internal pressure plus little bit pressure giving external pressure. So here external pressure is greater than internal pressure, so that the piston will move downwards. So it will move from here to here because both the pressure, external and internal, are different. They are separated by a small change in pressure. So the piston move from here to here. Okay. In a reversible process, external pressure is very much greater than internal pressure. That's why the piston move rapidly in a single step. But here, external pressure is very little bit greater than internal pressure. So the piston move from here to here. Right? Again, if external pressure is little bit, external pressure is little bit greater than internal pressure, again the piston move from here to here. Again, if external pressure is greater than internal pressure, it will move from here to here. Right? From this to this point to this point. Now, this process continues till the piston move from V1 to V2. Okay. So, total work done during the movement of piston from V1 to V2 is, we have to add work done in each step. dW plus dW plus dW plus dW plus dW etc 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 till V2. I think it's clear till here. Now, so work is equal to, total work is equal to dW plus dW plus dW plus dW etc 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 etc. Right? So total work when the piston moves from V1 to V2 is equal to, we have to add all the work done during each step. Now instead of adding, we have a mathematical function. That for mathematical function is known as integration. Instead of adding each and every term, dW plus dW plus dW, we have a mathematical term, and that term is known as integration. So W is equal to, instead of addition, we can use this mathematical function. This mathematical function is known as integration. Integration of dW from V1 to V2. That means we have to add dWs from V1 to V2. We have to add dWs from V1 to V2. We have to add all the dWs between V1 and V2. So, instead of addition, you can use this integration term, integration of dW from V1 to V2. This means we are going to add these value. Okay. So, integration, instead of addition, I am using integration of dW. We have to integrate dW. That means we have to add dW from where to where? From V1 to V2. Right? Now, W is equal to, now if the piston move from V1 to V2 rapidly in a single step, work done is minus P external into delta V. Here there is a large change in volume, right? So work will be W. Large work. But here work done during a single step. Work done during a single step is very less because volume change is very less. Here volume change is very less. So work done will be very less. So here dW, instead of W you can write integration of V1 to V2 minus P external into delta V. Once more, here in irreversible work done, equation to calculate irreversible work is minus P external into delta V. Here piston move from V1 to V2 rapidly in a single step. So there is a large change in volume. So work will be large. Work done by the piston will be will have a very large value because volume change is large. Same way, here work done by the piston in a single step is very small because volume change is very small. Volume change here to here, when the piston move from here to here, volume change is very less. So instead of W it is dW. Work done in this step is dW, right? So instead of dW you can write W is minus P external into delta V. So dW is equal to minus P external into dV. Small change in volume. For small work there is a small change in volume. For large work, large change in volume. For small work, small change in volume. So instead of dW we can write minus P external into delta V because work is minus P external into delta V. Here there is a large change, but here there is a small change. So small change, work done is dW. So for small work there is a small change in volume. So instead of dW I am writing minus P external into dV, small change. I think it's clear till here. So W is equal to minus P external into dV. Now please listen carefully. Now next step. We know that, I think it's clear. Now we know that external pressure is equal to internal pressure plus dP, right? External pressure is equal to internal pressure plus dP, which we have already discussed. External pressure is little bit greater than internal pressure. That is internal pressure plus that little bit pressure. Infinitesimally small change in pressure. Small pressure gives external pressure. So substituting this value instead of external pressure, you will get W is equal to integration of V1 to V2 minus P external into delta V. Instead of P external I am writing minus here. Instead of P external I am writing P external into delta V, right? Minus P external into dV. Instead of P external I am writing P internal plus dP. P internal plus dP. So instead of P external I am writing P internal plus dP. So minus P internal plus dP into dV. Now multiplying these terms with dV. So W is equal to integration of V1 to V2 minus P internal into dV plus P internal into dV plus dP into dV. dP into dV. P internal into dV plus dP dV. Right? I think it's clear. Now dP means small change in volume, small change in pressure. Small change in pressure. What is dV? dP and dV. What is dV? Small change in volume, right? When you multiply small change in pressure, that is dP, and dV, you will get a very small value, right? You will get a very small value because dP is very small change in pressure and dV is small change in volume. So when you multiply small pressure values with small volume value, you will get a small value. You will get a very small value. So that I am neglecting this part because dp dv always give a very small value. So we can neglect that part. It's very small value. So neglecting dp dv, reason small value. You will get w is equal to integration of v1 to v2 minus p internal into dv. Neglecting this value because dp small change in pressure, dv small change in volume. When you multiply two small value, you will get another small value, right? You will get a small value. So you can neglect this value because compared to p internal dv, it's a large value. Compared to this is very small value, so that we can neglect that value. So we'll get w is equal to integration of v1 to v2 minus p internal into dv. You cannot neglect this value. This is a very large value because this is pressure. Pressure will be a very large value. dp very small, dv very small. So these two are small compared to this value. So I'm neglecting that part. So you'll get you'll get w is equal to integration of v1 to v2 minus p internal into dv. I think it's clear till here. Okay. So we got w is equal to integration of v1 to v2 minus p internal into dv. Right. Now, this internal pressure is due to this gas. Which gas? Ideal gas filled in this cylinder. Internal pressure is due to ideal gas filled in this cylinder. So we know that for ideal gas, PV is equal to nRT. PV is equal to nRT. Here P is internal pressure, so I am writing P internal V is equal to nRT. For ideal gas, PV is equal to nRT. Now here pressure is P internal, so P internal V is equal to nRT. You know this equation to calculate ideal gas. Ideal gas equation. This equation is known as ideal gas equation. PV is equal to nRT. Here we are taking internal pressure as PINT. So PINT into volume is equal to nRT. So what is P internal? P internal is equal to nRT by V. P internal is equal to nRT by V. Substituting this value in this equation. Instead of P internal, I am writing nRT by V. You will get an equation like this. W is equal to integration of V1 to V2 minus nRT by V dV. Right. I am substituting P internal, value of P internal in this equation. So you will get W is equal to integration of V1 to V2. Instead of P internal, I am writing nRT by V minus nRT by V dV. Now, if we are conducting this process under constant temperature, that is isothermal condition. If we are conducting this process, if we are calculating or if we are doing this work under constant temperature, so process which take place at constant temperature are known as isothermal process. So we are conducting this work or we are doing this work under constant temperature. So under constant temperature, this work is known as isothermal work. Okay. So we are conducting work under constant temperature. So isothermal. So I am writing one more term here, isothermal. So we are going to calculate equation for isothermal reversible work, or we are going to derive equation for isothermal reversible work, because we are conducting this work, we are doing this work under isothermal condition. Under constant temperature, we are going to give a condition. Okay, so under constant temperature, that is isothermal condition, our reversible work will be isothermal reversible work. Okay, now we know that here temperature is constant. That is under constant temperature. So temperature become constant. Now what is our universal gas constant? So R is a constant one. R is constant. T is temperature. Temperature is constant because we are given that condition under constant temperature. That is temperature is constant. Now here R, what is our universal gas constant? So R is constant. Now here N is also a constant because we are conducting the process under in a closed system. Closed system means number of moles will not change. If we are conducting, I'm taking some water in this bottle. Since the bottle is closed, number of moles in this bottle remains constant because it cannot escape. If the system is open, if we consider open system, then due to evaporation, water molecule will escape, so number of moles decreases. But I'm taking a closed system. I'm taking a closed system so that number of moles in the system will not change. Number of moles remains constant. So here temperature remains constant, R remains constant, N constant. Okay. Now during integration, next step is we have to integrate. So during integration, W is equal to integration of V1 to V2 minus nRT by V dV. During integration, we have to take constant terms outside this integration. During integration, we have to take constant terms outside this integration. Here temperature constant, so I'm taking temperature outside integration, V1 to V2. R constant, I'm taking R outside this integration term. Here N is constant, I'm taking N outside this integration term, and minus. So minus nRT, integration of V1 to V2, 1 by V dV. Remaining term is 1 by V and dV. Okay, so I'm taking constant terms outside this integration. So T, R and N are constant. So W is equal to minus N R T integration of V1 to V2 1 by V dV. Okay, I think it's clear till here. So we got W is equal to minus nRT integration of V1 to V2 1 by V dV. Right. Now you should know how to integrate this value. Integration of 1 by x dx is integration of 1 by x dx is ln x. ln means natural logarithm. Now there are two types of logarithm. First one is natural logarithm. Natural log. That is, it is represented by ln. There are two types of logarithm. One is natural logarithm represented by ln, and second one is log to base 10. Log to base 10 represented by log. There are two types of logarithms, natural logarithm and log to base 10. When we integrate 1 by x dx, we will get ln x. When we integrate 1 by x dx, we will get ln x. 1 by x integration of 1 by x dx, we will get ln x. ln means natural logarithm. Okay. Now there are two types of log, natural log and log to base 10. Natural logarithm is represented by ln, and log to base 10 are represented by log. So integration of 1 by x dx is equal to ln x. When we integrate this term, we will get ln x. Now, so when we integrate, instead of x, if I am taking v, so integration of 1 by v, instead of dx I am taking dv, then 1 by x dx, integration of 1 by x dx is ln x. Then what is integration of 1 by v dv? You will get ln v, right? If integration of 1 by x dx is equal to ln x, then integration of 1 by v dv is ln v. So instead of integration 1 by v dv, I am writing w is equal to minus nRT. Integration of 1 by v dv is ln v. Okay. Now there are two limits, v1 and v2. So I am writing limit here, v1 and v2. Okay. When we integrate 1 by v dv, we will get ln v, and these limits v1 to v2, v1 from v1 to v2, I am writing here. I think it's clear till here. Now, integration of, please listen carefully, integration of 1 by x dx, limit x1 to x2. Integration of 1 by x dx, 1 by x dx from x1 to x2. When we integrate 1 by x dx under the limit condition x1 and x2, first we have to integrate 1 by x dx is ln x. Then we have to write like this, x1 x2, x1 x2. Okay. Then instead of x, you can write x2 first. x2 is known as upper limit and x1 is known as lower limit. Instead of x, first you put x2. So you will get ln x2. ln x, for this x we have to put this x2, upper limit. So ln x2. Now, next step, instead of this x, you can put this x1. This is known as lower limit, lower upper. Instead of, you can put x1. So you will get ln x1. So substituting upper limit instead of x, you will get ln x2. Substituting lower limit instead of x, you will get ln x1. Put a minus here. That is upper limit minus lower limit. First you put upper limit, then minus, then put lower limit. That is ln x2, upper limit, minus lower limit, ln x1. So integration of 1 by x dx from x1 to x2 is ln x2 minus ln x1. In a similar manner, similar way, you can integrate 1 by v dv. When we integrate 1 by v dv, we will get ln v. Now, if the limits are between v1 to v2, first we have to put upper limit. So you will get ln v2 minus, then lower limit, ln v1, ln v2 minus ln v1, upper limit minus lower limit. So w is equal to minus nRT. I am putting upper limit first. So you will get ln v2 minus lower limit, ln v1, upper limit minus lower limit. First put upper limit, then subtract, minus, then lower limit. I think it's clear. I think it's clear till here. No doubts? Okay. Now, ln A plus ln B. ln A plus ln B. Natural logarithm of A plus natural logarithm of B. You can write like this, ln A plus ln B. You can write ln A plus ln B like this, ln A into B. ln A into B. This is a formula of logarithm. ln A plus ln B is equal to ln A into B. It's a mathematical formula for logarithm. ln A plus ln B is equal to ln A into B. Now, ln A minus ln B is equal to ln A by B. ln A minus ln B is equal to ln A by B. ln A plus ln B is equal to ln A into B. ln A plus minus ln B is equal to ln A by B. Similar, this like same way, you can write ln V2 minus ln V1 like this. W is equal to minus nRT ln A minus ln B will be equal to ln A by B. So you will get here ln A by LB, that is V1. So W is equal to minus nRT ln V2 by V1. Okay, this is the equation. This is the equation to calculate isothermal reversible work. This is the equation to calculate isothermal reversible work. W is equal to, this is the equation to calculate isothermal reversible work. Isothermal reversible work or work. Isothermal reversible work. W is equal to minus nRT ln V2 by V1. Okay. Now, while doing problems by using this equation, it is very difficult to calculate ln. Okay, it is very difficult to calculate ln. So, for doing mathematical problems, instead of ln, we will use log. Instead of ln, we can use log. Okay, this is the equation to calculate isothermal reversible work. Now the problem is, while doing problems, it is difficult to calculate natural logarithm. So it is better to convert natural logarithm to log. Okay, there are so many easy methods to calculate problems by using log. So I am going to convert ln to log. Now ln is equal to 2.303 log. This is the relationship between ln and log. ln is equal to natural logarithm is equal to 2.303 log. This is the relationship between natural logarithm and log to base 10. ln is equal to 2.303 log. So instead of ln, I am writing log. So we will get W is equal to minus nRT. Instead of ln, I am writing 2.303 log. 2.303 log. Okay. Instead of ln, I am writing 2.303 log. Okay. Into V2 by V1. So this is the equation to calculate isothermal reversible work. You can learn this equation. This is the equation to calculate isothermal reversible work. Now, why we convert ln to log? For doing problems, while doing problems, it is very difficult to calculate ln value. Okay, so it is better to convert this ln to log. You can easily calculate log values by using calculators or by using Clark's table. You can easily calculate log values. Okay, but ln value, to calculate ln value, we need something else. So it is better to convert ln to log. So I am converting ln to log. Ln is equal to 2.303 log. So W is equal to minus 2.303 nRT log V2 by V1. So this is the equation to calculate isothermal reversible work. So last class we discussed about irreversible work, and today we discussed about isothermal reversible work. Isothermal reversible work. Isothermal reversible work. So for irreversible work, first one, irreversible work, workers W is equal to minus P external into delta V. Here the piston move from, since external pressure is very much greater than internal pressure, the piston move from V1 to V1 volume, V1 to V2 volume, right? So work done during this change, when the piston move from V1 to V2. So work done during this change is irreversible work. When the work done during a single step, that is irreversible work. W is equal to minus P external into delta V. So irreversible work means when external pressure is very much greater than internal pressure, the piston move from V1 to V2, right? So in a single step, rapidly. So work done during this change is known as irreversible work. Equation W is equal to minus P external into delta V. Now B, reversible work. Equation W is equal to minus 2.303 nRT log V2 by V1, right? Now here the piston moves from V1 to V2 V1 to V2, not in a single step, by taking so many steps, infinite number of steps, okay. Here external pressure is dP amount greater than internal pressure, external pressure is dP, small amount greater than internal pressure, okay, dP amount greater than internal pressure. So this is the equation to calculate isothermal reversible work. Isothermal reversible work, because we consider isothermal condition during reversible work. So we consider isothermal condition during this reversible work. So this isothermal reversible work. This is the equation to calculate isothermal reversible work. Now, both irreversible work and reversible works, both in the case of irreversible work and reversible work, you can see pressure and volume change. Due to high pressure, due to high external pressure, volume is changing. Due to high external pressure, volume is changing. So both these reversible and irreversible work are pressure volume change work. Pressure volume change work. So here the work is carried out due to pressure and volume change. So both irreversible and reversible work are pressure volume change work. I think it's clear. In both these cases, pressure, due to high pressure, volume is changing. As a result, we are observing a work. Okay. So both the process are, in both the process there is a pressure, that work is pressure volume change work. In thermodynamics we always deals with pressure volume change work. We always deals with pressure volume change works. In thermodynamics we always deals with pressure volume change work. I think it's clear till here. Moving on to next topic, free expansion. Now, what does mean by free expansion? Free expansion means expansion in vacuum. Expansion in vacuum. Expansion is vacuum. Expansion in vacuum is known as free expansion. Now, for free expansion, external pressure is equal to 0. So, free expansion means expansion in vacuum, and for free expansion, external pressure is equal to 0. Now, there are two types of work, irreversible work and isothermal reversible work. Now, we know that in the case of irreversible expansion work, let the internal pressure be P internal, external pressure is P external. Now, under free expansion condition, external pressure is equal to 0. So that here internal is greater than external pressure, the piston will move upwards, right? The piston will move upwards. Okay. Now, what will be work? Work is equal to, what is the equation to calculate irreversible work? Minus P external into delta V, that is W is equal to, here in the case of free expansion, external pressure is equal to 0, 0 into delta V, that is W is equal to 0. So, work is equal to 0. Work will be equal to 0 in the case of irreversible work under free expansion condition. So, under free expansion condition, that means expansion in vacuum, external pressure is equal to 0. Under free expansion condition, external pressure will be equal to 0. So, irreversible work will be equal to 0. I think it's clear. Now, free expansion in the case of isothermal reversible work. Now, what is the equation to calculate isothermal reversible work? W is equal to minus 2.303 nRT log V2 by V1. This is the equation to calculate isothermal reversible work. Now, under free expansion condition, that is free expansion, external pressure will be equal to 0. Now, we got this equation for isothermal reversible work. We got this equation for isothermal reversible work by integrating this equation. I think you remember the derivation. By integrating this equation, we got this equation, right? Now here in this equation, external pressure, we have a term related with external pressure, we have a term with external pressure, P external. So when in the under free expansion condition, external pressure is equal to 0. When we put 0 here, we will not get this value, we will get integration of 0 dV, which will be equal to 0. So under isothermal in the case of isothermal reversible work, under free expansion condition, work will be equal to 0. I think it's clear. Please listen carefully. Equation to calculate isothermal reversible work is W is equal to minus 2.303 nRT log V2 by V1, and we got this equation from this one, right? From this equation we got this equation. You still remember the derivation. We are substituting some values for P external, then we got, by doing integration everything, we got this equation, right? Now for under free expansion, external pressure is equal to 0. So when we integrate this equation by putting some values here for P external, we got this equation. Now if external pressure is equal to 0, W will be equal to 0 into dV V1 to V2, which is equal to 0. So for both irreversible work and isothermal reversible work value will be equal to 0 under free expansion condition. Under free expansion condition, both reversible work and isothermal reversible work W value will be equal to 0. Okay, please remember this topic. Okay, moving on to next topic. Calculation of heat, work and change in internal energy under isothermal and free expansion condition. So under isothermal and free expansion condition, we are going to calculate Q, heat, W, work, and delta U, change in internal energy under both these conditions, isothermal and free expansion condition. I will start with the isothermal condition. Under isothermal condition, irreversible process, under isothermal condition for irreversible process, we know that W is equal to minus P external into delta V, right? Now for isothermal condition, you should remember that for isothermal condition, delta U, change in temperature, will be equal to 0 and change in internal energy will be equal to 0. Both these terms will be equal to 0. For isothermal condition, initially in our introductory topics, we learned that isothermal, that is constant temperature. For isothermal process, delta T will be equal to 0. This we have learned in our introductory topic. Now adding one more thing. For isothermal process, both the terms, that is delta T will be equal to 0 and change in the internal energy, delta U, both these terms will be equal to 0. Both these properties, delta T and delta U, will be equal to 0 in the case of isothermal process. So isothermal condition, for reversible process, W is equal to minus P external into delta V. For irreversible process, work is equal to this much. And delta U, since it is isothermal process, delta U is equal to 0, right? Now, according to first law of thermodynamics, delta U is equal to Q plus W. Since delta U is equal to 0, this is 0. So what will be the value of Q? Q is equal to Q. I can take W here, that is minus W. So which be equal to minus of, what is the value of W? Minus P external into delta V. Minus of P external into delta V, minus you will get plus P external into delta V. I think it's clear. Once more, for isothermal condition, both these thermodynamic properties, that is delta T and delta U, will be equal to 0. Now, in the case of irreversible process, work is minus P external into delta V. Okay. Now, what is delta U? Work is equal to minus P external into delta V, because for irreversible process, equation to calculate work is minus P external into delta V. Now, for isothermal process, delta U is equal to 0. So what will be Q? Q will be equal to, according to first law, delta U is equal to Q plus W. Here, delta U is equal to 0. Delta U is equal to 0. So 0 is equal, we will get 0 is equal to Q plus W. So that I am taking W to left side. So Q is equal to, I am taking this W here. So Q is equal to minus W, that is minus of minus P externally delta V. W is minus P externally delta V. So minus W is minus of minus P externally delta V, minus minus, you will get plus value. I think it's clear. Now B, for reversible work. Now for reversible process. Now for reversible process, W is equal to minus 2.303 nRT log V2 by V1. Right. Now, under isothermal condition, delta U is equal to 0. Change in internal energy is equal to 0. Right. Always under isothermal condition, delta T and delta U will be equal to 0. So delta U is equal to 0. Now, according to first law of thermodynamics, according to first law of thermodynamics, we know that delta U is equal to Q plus W. So Q is equal to, since delta U is equal to 0, so 0 is equal to Q plus W. Q is equal to minus W, which is equal to minus into, what is W? Minus 2.303 nRT log V2 by V1. Minus into minus, you will get a plus value. So 2.303 into V2 nRT by log V2 by V1. This is equal to Q. So we calculated W and delta U and Q. W, delta U and Q for irreversible and reversible process under isothermal condition. Right? Isothermal condition. Moving on to next condition, free expansion condition. So next condition, free expansion. Next condition, free expansion. Now under free expansion condition, W will be equal to 0, which we discussed earlier. For free expansion condition, W is equal to 0 for irreversible and reversible process. So W value will be equal to 0. Okay, W value is equal to 0. So according to first law, W value is equal to 0. So according to first law, we can write delta U is equal to Q plus W. Since W is equal to 0, we will write delta U is equal to Q. Delta U is equal to Q. Right? Delta U is equal to Q. Now, for reversible process also, W is equal to 0. Since under free expansion condition, W is equal to 0. Now, so according to first law, delta U is equal to Q plus W. Since W is equal to 0, you will get delta U is equal to Q. Okay, so we calculated heat, work and delta U. Heat, work and delta U under isothermal condition for reversible and irreversible process. And under free expansion condition for reversible and irreversible process. I think it's clear. So I'll explain one more process under adiabatic process. I'll explain one more process. Adiabatic process. Please listen carefully. Isothermal condition. Isothermal condition for adiabatic process. What is adiabatic process? Adiabatic process in which there is no exchange of heat between system and surrounding, which we have already discussed in our introductory topic. Adiabatic process means Q is equal to 0. There is no exchange of heat between system and surrounding. If system and surrounding, if they are not exchanging heat energy, those processes are known as adiabatic process. For adiabatic process, Q is equal to 0. So first term, Q is equal to 0. So according to first law, delta U is equal to Q plus W. Now, since it is isothermal process, delta U will be equal to 0, right? So delta U will be equal to 0. So since it is isothermal, so we are considering adiabatic process under isothermal condition. We are considering just before this we considered reversible and irreversible process under isothermal and free expansion condition. Now we are considering adiabatic process under isothermal condition. Isothermal condition means delta U is equal to 0. Adiabatic process del Q will be equal to 0. So Q will be equal to 0 and delta U will be equal to 0. So according to first law, these two value will be equal to 0. So obviously W will be equal to 0. Delta U 0, Q 0, so W will be equal to 0. Now, free expansion condition. Free expansion condition for adiabatic process. Adiabatic process. We know that free expansion means W is equal to 0. Adiabatic process Q is equal to 0. So here W is equal to 0, Q is equal to 0. So according to first law, delta U is equal to Q plus W. Here Q is equal to 0, W is equal to 0. So delta U will be equal to 0. So we consider three process. First one, reversible process under two conditions, isothermal and free expansion. Then we consider irreversible process under two conditions, isothermal and free expansion condition. Third, we consider third process, adiabatic process under isothermal condition and free expansion condition. Here for adiabatic process under isothermal condition, all the values delta U, Q and W will be equal to 0. Delta U, Q and W equal to 0. And in free expansion condition for adiabatic process, both the three values will be equal to 0. Delta W is equal to 0, Q is equal to 0 and delta U is equal to 0. I think it's clear. I think it's clear till here. Okay. I think it's clear till here. So you have to remember these topic. Okay. So next topic is enthalpy. So till then, see you. Bye.